Thank you. Uh, Good afternoon, ladies and gentlemen. It's my pleasure to be here. VTT is a technical research center of Finland. It's a government organization, pretty much like NIST. And during the last few years, we have been studying the modeling of water mist systems. Water mist systems have been used commercially about maybe 20 years now. And over that time, the suppression performance of these systems has been demonstrated almost entirely by full-scale testing. And usually these tests look like something like that on the screen, so you don't see actually much. Over that 20 years period, computational models have been available, models of different ranges of complexity, but still these models have mainly been used for marketing, for selling the systems, or for academic studies, not so much for designing or sizing the system itself. But the full-scale testing is really expensive, and manufacturers of these systems have realized that if you want to design a systems for a situation like that here in the picture, for a road tunnel, for example, you really want to have a model that you can use to extend the range of applications that you have been able to demonstrate in full-scale tests. So you want to use the model that has been, in some sense, validated, and you have a system that has been shown to work well in a full-scale test that is smaller than your application. There are several challenges in performing these simulations. There are numerical challenges, computational. These are going to be big calculations because you have to solve the transport, evaporation of a huge number of water droplets. It's challenging from the physics viewpoint because the suppression mechanisms, there are more suppression mechanisms in water mist system than with conventional sprinklers. We have to deal with surface wetting, gas phase extinction, and the blocking of radiation. And also, it's not straightforward to characterize the water mist sprays in terms of the quantities that we need to specify as boundary conditions for the computation. So a few years ago, we started to work on FDS modeling of these systems. Both wanted to see that we wanted to see how can we characterize the sprays and create the input files, and also we wanted to validate some of the capabilities of FDS. So in this talk, I go through some of these results and start from the spray computation. The transport of water droplets is the same method that has been used in FDS for all these years. We saw the movement and evaporation of Lagrangian particles. Now, over the last few months or maybe 2 years or so, the actual numerical method to solve the transport has developed. Randy and Howard Baum of NIST developed a new analytical solutions for the momentum transfer between droplets and gas phase. And on the slide you can see one of the verification cases. So we can and we want to show that we transfer a correct amount of momentum from a particle or a group of particles to the gas phase. The drop size distributions are still the same hybrid distributions functions that have been used for sprinkler simulations for years. Now, when we deal with water mist systems, we have to think about some model assumptions of the model that we haven't thought so much before. For example, in some situations, the water sprays may be so dense that the individual droplets are no longer separated by each other with so long distance that they don't actually know anything about each other. But instead, they start to feel the wakes of each other, and we want to consider the reduction of drag force due to this wake. And so we implemented a correlation for the drag reduction to see if it makes a big difference. And this kind of correlation, it doesn't take too much computational effort to calculate it. And I can already say that in most of these simulations we did, and I'm going to talk here about, it actually didn't do much. It didn't have a huge impact on the results. But still we want to keep it there because it may happen that if someone wants to simulate a water spray really close to the nozzle, directly to the region where the breakup processes take place, then the drag forces are going to drop significantly. This is just an example of the features of the model that or the assumptions that we need to reconsider when we expand the application from relatively low speed, low density water sprays to very fine, high momentum sprays. Okay, how we introduce the droplets to the computation. The droplets are introduced on a segment of a spherical surface using a probability function or distribution. You can, oops. So here you would see the surface, and you can specify various functions. Even you may want to have a flat profile or something very specific to your nozzle. But in our case, we found out that Gaussian distribution gave the best description of the water density inside these commercial water mist sprays. The initial velocity of the droplets is calculated directly by user. It's given specified by the user, but we calculate it from the pipe pressure. And one parameter here is the offset from the nozzle to this surface where we introduce the droplets into the computation. That's something that the user has to specify. And unfortunately, in some of these calculations, it turns out to be quite important to the results. So if you are used to do sprinkler computations, maybe it didn't matter so much, but now it may actually be an important parameter to look at. In this work, we considered 4 different micro nozzles. One was LN2 nozzle from spraying systems, and then we had 3 high-pressure micro nozzles from Marriott Corporation, here denoted as A, B, and C. From the table over there, you can see the K factors that tells how much water comes out of the nozzle, the width of the spray in terms of angle, degrees, and then the parameters of the drop size distribution. Then we also looked at multi-orifice spray heads that you can see in the picture over there. They are basically, these would be the ones that you would see in a ceiling of a compartment that is where the water mist system is installed. So they are basically a piece of metal which has been attached with several of these micro nozzles. So we studied 5 different types of multi-orifice spray heads with different combinations of A, B, or C, and different angles between the central and the surrounding nozzles. The experimental work on spray characterization was actually done at the university, Tampere Technical University in Finland, by another group. They used direct imagining technology to measure the radial profiles of drop size, velocity, and mass flux, water mist mass flux. The measuring locations were determined according to the NFPA 750 standard. And here we can see some results for the LN2 nozzle. The top left, you see the profile of spray or water velocity or speed of droplets, and the simulation with 3 different spatial resolutions. The spatial resolutions are here 1, 2, and 4 centimeters. So you immediately can see that we are talking about quite different resolutions that might be used in typical engineering analysis of a complete road tunnel or something. But okay, as Randy discussed, here we want to see how well the model works in a very well resolved calculations. Okay, and you can see that some of these profiles are actually quite well converged, but there are details that are not. For example, that drop velocity on the spray axis is not very well converged. Top right, you can see the mean drop size profile, showing this kind of a profile where the small droplets are concentrated on the axis of the spray, and larger droplets are concentrated to the outer edge of the spray, which means that the large droplets have enough momentum to continue and they remain on the outer edge, but the entraining air will bring and collect the small droplets to the center of the spray. Okay? And the last figure, you will see the water mist mass flux distribution, which doesn't show perfect in the axis. Outer parts of the spray are pretty good. And similar results for the micronozzles A, B, and C here combined. These were 2 centimeter resolution calculations. I'm sorry, the drop speed figure has different signs. So now it's just showing the velocity as positive number. Okay, again we see that they are quite nice, but what is important here is that the drop size profile is not that V shape anymore. Instead, it's actually pretty flat distribution. And so this is the essential difference between the LN2 nozzle and these nozzles. These nozzles have very much higher velocity. The spray is much more turbulent. And this fairly good computational result was only possible after we introduced the dynamic turbulence model into FDS. Before that, FDS could not predict that flat profile. It would give that kind of V-shaped profile for these nozzles too. Okay. Another important capability of the water mist system is to move the air, to mix the space, to penetrate the water into the hot fire zone. So it is important that FDS model can predict the entrainment of air, how much the water droplets make the air to move. And so we had made this kind of simple experiment in our laboratory where we built a rectangular channel of 2 meters long, 0.6 meters wide and height. And we placed each of these multi-orifice nozzles in the middle of the channel. We ran the experiments at 3 pressures from 50 to 100 bar and measured the airspeed upstream from the nozzle in the middle of the channel and also close to the channel wall. And here you can see the comparison of the measured and predicted steady state airspeeds. The channel central results on the left and the closer to the wall results on the right. And okay, what's important here is that FDS can correctly predict the dependence of the difference between the most of the spray heads, so how much water comes out from the nozzle has the correct effect on the airspeed. It can also predict how much the changing pressure from 50 to up to 100 bars is going to change the airspeed in the channel. So the entrainment is captured. Some of the results are not captured accurately, and those are related to the spray heads 4 and 5, where the only difference is the angle between the central and the surrounding nozzles. So meaning that when the angle gets very narrow, it is going to have a higher push of momentum to the gas phase. And this becomes very difficult to capture because you need very good resolutions to capture the flow of these individual sprays that have very small angle between them.
So I'm afraid that you have to keep moving.
Yeah. Okay.
Maybe your last slide.
Yeah. So I will show the radiation. This was the final experimental theory I'm going to show here. So we measured the radiation attenuation, and this is the kind of stuff that goes into the validation guide. So we can show what is the bias and what is the deviation of the radiation attenuation measurements. When we have very well resolved case, we are close to the experimental uncertainty here. So the last slide, I would like to acknowledge the people from Tampere and also the whole team of FDS developers and these companies and agencies for funding. Thanks.
We have time for just one quick question, perhaps. In the back.
Hi. I just wanted to check, has there been any validation done with the mist particles are very fine? What is the effect of the strong draft coming in to the compartment? Has there been any validation done on that?
Draft from
Anywhere.
From
Be it natural or mechanically ventilated source?
well, I was going to show a case where we placed these spray heads in the our test hall and measured the movement of spray in a very long distance, but up to this point we haven't been able to finish that work. So I'm not sure if there is such a validation already using the current version of the model. Yes, Coast Guard test validate some of the features, but we haven't really looked. We looked at the suppression result and have been focused on the suppression times and heat release rates. And so far we haven't been able to distinguish between the various effects, if it's mixing or draft or just the gas phase suppression extinction. Okay.
Thanks again, Simo.
Yeah.